know what's wild? In 1971, two physicists walked into an airport carrying the most precise clocks humanity had ever built. They bought regular commercial airline tickets, coach class, probably, and flew those clocks around the entire world. When they came back and checked the time, those clocks had lost nanoseconds compared to identical clocks that stayed on the ground. They had just proven that time itself bends. I'm talking about the Hafele-Keating Experiment, and it's one of the most elegant, audacious, and frankly bizarre experiments in the history of physics. Because here's the thing, they didn't just prove Einstein right. They proved that everything you think you know about time, that it flows the same for everyone, everywhere, always, is wrong. But let me back up, because to understand why this experiment matters, we need to talk about the man who broke time in the first place. The year is 1905. Albert Einstein is working in a patent office in Bern, Switzerland. He's 26 years old, couldn't get a job at a university, and is spending his days evaluating other people's inventions. And in his spare time, he's rewriting the rules of the universe. That year, Einstein publishes his paper on special relativity, and buried in the mathematics is an idea so strange, so counterintuitive, that even today it feels wrong. Time is not absolute. Time is not the same for everyone. If you move fast enough, time slows down for you. This is time dilation, and it means that two people can experience time at different rates, depending on how they're moving. A person on a spaceship traveling near the speed of light would age more slowly than someone standing still on Earth. It's not an illusion. It's not a trick. Their clocks would actually run at different speeds. Now, when Einstein first proposed this, people thought he was insane. Time, after all, is time. A second is a second. An hour is an hour, right? Wrong. But here's the problem. In 1905, Einstein had no way to prove it. The differences in time that relativity predicted were so incredibly tiny at everyday speeds that they were impossible to measure. You'd need clocks accurate to billionths of a second. You'd need to move really fast, and you'd need to compare them directly. In 1905, this was science fiction. But then came atomic clocks. Let me tell you about atomic clocks, because they're honestly one of the most insane pieces of technology humans have ever created. Your watch, your phone, they lose seconds over time. They drift. But an atomic clock measures time using the vibrations of atoms, specifically cesium atoms, and these vibrations are so perfectly regular, so unchanging, that an atomic clock can run for millions of years without losing a single second. By the 1960s, atomic clocks had become so precise that they could measure time down to nanoseconds, billionths of a second, and suddenly, the tiny time differences that Einstein predicted weren't theoretical anymore. They were measurable. And that's when Joseph Hafele and Richard Keating had an idea. Hafele was a physicist at Washington University. Keating worked at the United States Naval Observatory, which at the time housed some of the most accurate atomic clocks in the world. And one day, Hafele realized something. We don't need a spaceship. We don't need to go near the speed of light. We can test time dilation right here on Earth. Because there are two ways time can slow down, according to Einstein. The first is speed. Move fast enough and time dilates. This is special relativity. But the second way is gravity. The stronger the gravitational field you're in, the slower time moves. This is general relativity, which Einstein published in 1915. And here's where it gets really interesting. If you take an atomic clock, put it on a commercial airplane, and fly it around the world, two things happen. First, the plane is moving fast. hundreds of miles per hour. So special relativity says time on the plane should run slower than time on the ground. But second, the plane is flying high, where gravity is slightly weaker, so general relativity says time on the plane should run faster than time on the ground. These two effects work against each other, but Einstein's equations tell you exactly how much. You can calculate the difference down to the nanosecond. So Hafele and Keating proposed an experiment. Take atomic clocks on commercial flights around the world, bring them back, and see if the time matches Einstein's predictions. It sounds simple. It wasn't. First of all, atomic clocks in 1971 weren't exactly portable. These things were massive, delicate, and absurdly expensive. The clocks Hafele and Keating used were cesium beam atomic clocks, and each one weighed about 60 pounds and was housed in a protective case. They needed constant power. They were sensitive to temperature, vibration, and electromagnetic interference, and they were planning to strap these things into the cabin of a passenger jet and fly them tens of thousands of miles through turbulence, temperature changes, and cabin pressure variations. Oh, and they needed 4 clocks, one for each flight, plus backups. The United States Naval Observatory agreed to lend them the clocks. Then came the next problem: money. Flying atomic clocks around the world isn't cheap. They needed to book seats on commercial flights, multiple routes. Eventually they got funding, and in October 1971, Hafele and Keating packed up their atomic clocks, headed to the airport, and did something that had never been done before. They put time itself to the test. The experiment had 2 parts. First, they flew eastward, in the direction of Earth's rotation. Then a few weeks later, they flew westward, against Earth's rotation. The reason for this is brilliant. Flying east means you're moving faster relative to the center of the Earth because you're moving with the planet's rotation. Flying west means you're moving slower. So the time dilation effects should be different in each direction. Einstein's theory made specific predictions. Flying eastward, the clocks on the plane should lose about 40 nanoseconds compared to clocks on the ground, mainly because of the speed effect. Flying westward, the clocks should gain about 295 nanoseconds because the altitude effect outweighs the speed effect when you're flying against the rotation. These are absurdly small numbers. We're talking about differences measured in billionths of a second. But if Einstein was right, those differences should be there. So Hafele and Keating boarded their flights. They sat in the cabin with their atomic clocks. They flew from Washington, D.C. to London, to Frankfurt, to Beirut, to Tehran, to New Delhi, to Bangkok, to Hong Kong, to Tokyo, to Honolulu, and back to Washington. Tens of thousands of miles, multiple stops, multiple time zones, and the whole time, those atomic clocks were ticking, measuring every nanosecond. When they got back, they compared the traveling clocks to identical clocks that had stayed at the Naval Observatory. And you know what? Einstein was right. The eastward flying clocks had lost 59 nanoseconds. The westward flying clocks had gained 273 nanoseconds. The numbers weren't perfect. There was some experimental uncertainty, some noise in the data, but they were within the margin of error of Einstein's predictions. Time had actually slowed down. Time had actually sped up. And they had measured it. Now, I need you to really sit with this for a moment, because what this means is profoundly weird. When those clocks flew around the world, they didn't just measure time differently. They actually experienced time differently. Less time passed for the eastward flying clocks. More time passed for the westward flying clocks. If you could somehow perceive time at that level, the universe would literally feel different depending on whether you were on the ground or in the plane. This isn't philosophy. This isn't abstract theory. This is measured, documented reality. And it means that the time on your wrist right now, the time you're experiencing as you watch this video, is different, ever so slightly, from the time someone on an airplane is experiencing, or someone at the top of a mountain, or someone in the basement of a building. GPS satellites have to account for this. They're moving fast, and they're high above the Earth, so time runs differently for them than it does for us. If we didn't correct for time dilation, both from speed and from gravity, GPS would be off by miles within a day. Every time you use Google Maps, you're relying on Einstein being right. But here's the thing, the Hafele-Keating experiment almost didn't work. There were problems, lots of them. The clocks were sensitive to vibration, and airplanes vibrate. They were sensitive to temperature, and cabin temperatures fluctuated. There were delays, missed connections, route changes. At one point, one of the clocks started malfunctioning and they had to troubleshoot it mid-flight. And then there was the scrutiny. When Hafele and Keating published their results in 1972, not everyone believed them. Some physicists questioned the methodology. The error bars were relatively large. Nanoseconds are hard to measure, and there were a lot of variables. Critics said the experiment was too messy, too imprecise. But here's what's important. They repeated it. Other teams ran similar experiments with better clocks, better controls, more data. And every single time, Einstein's predictions held up. In 1976, a more precise experiment was done with atomic clocks on airplanes. In 2010, scientists measured time dilation over differences in height of less than a meter, less than 3 feet, using the most advanced atomic clocks ever built. Every time, relativity wins. So why does this matter? Why should you care that a couple of physicists flew some clocks around the world 50 years ago? Because it tells us something fundamental about reality. It tells us that time is not what we think it is. Time is flexible, time is relative, time is woven into the fabric of space itself, bending and stretching depending on how fast you're moving and how deep you are in a gravitational field. It means that when astronauts go to the International Space Station and come back slightly younger than they would have been on Earth, and yes, this is real, this has been measured, that's not science fiction, that's just physics. It means that time travel isn't just possible, it's happening all the time. Not the dramatic, Hollywood kind, where you jump into a machine and appear in the past, but the real kind, where you move through time at a different rate than someone else. We're all time travelers. We just don't notice it because the effects are so small at human speeds. But they're there, and the Hafele-Keating experiment proved it. There's something poetic about this experiment, don't you think? 2 guys with 4 atomic clocks, sitting in coach on commercial flights, sandwiched between tourists and business travelers, quietly conducting one of the most important experiments in the history of physics. No billion-dollar particle accelerator, no massive telescope, just precision, patience, and the audacity to ask, what if Einstein was right? And he was. Time bends, time stretches. Time is not the universal constant we thought it was for thousands of years. And somewhere in the universe right now, there are places where time moves so slowly that a second for us might be years for them. Black holes, where gravity is so strong that time nearly stops. Neutron stars, the edges of the observable universe. The Hafele-Keating experiment didn't just prove a theory. It opened a door. It showed us that the universe is stranger, weirder, and more beautiful than we ever imagined. And all it took was 4 atomic clocks and 2 plane tickets. So the next time you're on a flight, think about this. You're not just traveling through space. You're traveling through time, just a little bit differently than everyone on the ground. The universe is bending around you. Time itself is shifting. And thanks to Hafele and Keating, we know it's real. Pretty wild, right?